Hello and welcome to this video on lithium-ion cells, which are becoming increasingly popular. The photo you can see here is a lithium battery that might go into a calculator. In a different shape it would go into your phone, and in a big version of it is even going into electric cars now. So many applications for lithium batteries, mainly because they're 3-volt batteries, which is quite a high voltage for a little cell. Now, you need to know how they work, and that's going to come up on the following slides. But the basics of it is that you're doing this reaction. You're starting off with some lithium metal, and you're letting it react with cobalt dioxide. And when it does so, you get lithium cobalt dioxide. If you let that happen in the format of a cell, you're going to get an EMF of about 3 volts, as is given here. So that's the overall reaction, and you can see that lithium is going from an oxidation number of 0, because it's a metal, to +1 here, and cobalt here is +4 there and +3 here. So lithium's being oxidized, cobalt's being reduced on discharge, and then when you're recharging it, obviously the opposite is going to happen. But in order to get those 3 volts out of this reaction, of course we have to set up 2 half reactions, which enable us to strip the electrons off the lithium, make them go around a circuit so that they can do some work for us, like run a laptop or a phone, whatever. Okay, so let's have a look at the half reactions and the electrodes. Okay, so let's build up the cell from scratch. First of all, let's have a look at the negative electrode. All right, so here we've got some graphite strips. So this is the negative electrode. This is the negative electrode, and you remember from no PR that this is where oxidation occurs. And what we have is some lithium metal. All right, so let's draw some red circles here to represent lithium metal atoms. In between the strips. Doing this as fast as possible, thanks for bearing with me. So we've got lithium metal atoms here, and let's have a look at the other electrode. So let's write down first that this is the positive electrode. And discharge. So the positive electrode, this is where reduction is going to happen. But as we said in the previous slide, this is a reduction of cobalt, not lithium. So let me explain these blue and green circles. Didn't I say that the electrode was cobalt dioxide? Right, so we've got cobalt dioxide. So these blue circles are representing oxygen ions, and the green are the cobalt ions. So that's oxygen and cobalt, and they're arranged in the ionic lattice like they are. And so you can see there's twice as many oxygens as cobalts. Okay, so that's the setup. Now let's just have a think, and let's attribute some sort of thinking power to these metal atoms. Going back to the negative electrode, these red lithium atoms, they're not really keen on their outer electron, are they? But these poor cobalt ions, these are cobalt 4+ ions, and these are oxygen 2- ions in the structure there. So cobalt's been stripped of 4 of its electrons, and it's It's not really happy about that. That's been overdone. It would prefer to be cobalt 3 plus ions. And lithium on the other side, those lithium atoms would they don't mind being lithium ion 1 plus ions. All right, so that's the little electromotive difference that's going to drive this cell. The fact that cobalt 4 plus ions are not really happy being 4 plus ions, they want to be 3 plus ions, and lithium is quite happy being lithium 1 plus ions. Okay, so what you do is you provide them with a medium where they can, so they can react, and that's a bunch of, so the electrolyte, which is that medium I just referred to. The electrolyte here is in fact just a lithium salt. All right, so you've got lithium ions in a solvent. It's actually an organic solvent. Okay, so remembering back, we've got some lithium atoms, all right, and lithium atoms that quite fancy being lithium 1 plus ions, and we've got some cobalt 4 plus ions there in the positive electrode that quite fancy being cobalt 3 plus ions, and the electrolyte just facilitates the that reaction there. So we've got these lithium atoms, and what happens is they turn into lithium ions. Let's draw them like that. Well, let's even label them lithium 1 plus ions, and so that electron that's lost goes around. Let's say that electron goes around in that direction, and the lithium ions go across from one electrode to the other through the electrolyte. Okay, so they go along and they find their way into a space in the lattice, and that happens with that ion. So this this cobalt 4 plus ion can now be a cobalt 3 plus ion, because this electron has gone around the circuit in this direction, made its way over to this electrode, and so that goes from a cobalt 4 plus to a cobalt 3 plus. The oxygen is still happy, it doesn't really care because it's still oxygen 2 minus, and that's facilitated by the fact that lithium 1 plus ion has taken its place in that lattice. So it's still a neutral compound. So this has this part of the lattice has turned. Let's just draw a little. Let's change colour. Right, I'm going to draw a little circle around this part of the lattice here, right, and that has become not cobalt dioxide, but lithium cobalt dioxide, right, through that reaction. Now let's do it again, just to be safe. Okay, we'll take this lithium atom here that I've just coloured in. All right, that turns into a lithium 1 plus ion, another electron, goes around the circuit. Yeah, so this lithium 1 plus ion, let's say it goes into here. Okay, that electron's gone around the circuit and allows this cobalt 4 plus ion to turn into a cobalt 3 plus ion, but the compound is still neutral, because if we take that part of the lattice, instead of being so it was cobalt dioxide and it's now lithium cobalt dioxide. So that's essentially what's happening intuitively. Now why don't we write down the half reactions that are happening at that time. So I'm going to go to green for the half reactions, why not? So at the negative electrode, we'll do the half reactions at the top. We've got draw it in the oxidation reaction, in the oxidation direction, because that's the reaction that actually happens. So you've got some lithium that turns into lithium 1+ ions plus the electron. That's the reaction that actually happens. But let's do the reduction reaction, because that's how we write it as a half cell. So you've got lithium 1+ ion plus an electron is going to lithium solid, and the standard electrode potential of that half reaction is -3.04 volts. So there we have it. Now let's go over to the positive electrode where the reduction is happening. And so that lithium ion turned up, didn't it? It's a lithium ion, and it's reacted with the cobalt dioxide, and we got a reduction reaction where we got lithium cobalt dioxide. And of course we needed the electron plus the electron there that came around this circuit that I've drawn in the red line there. And that we can leave in green, because that is the reduction reaction that happens. And the standard electrode potential of that reaction is about 0.36 volts. So if we do E cell, as you remember, it's the electrode potential of the reduction reaction minus the electrode potential of the oxidation reaction. So the reduction reaction is 0.36. The oxidation reaction is -3.04. And so the E cell is about 3.40 volts, which is quite a nice voltage compared to other cells like the typical alkali batteries are 1.5 volts, of course. So hopefully that's helped you understand how the lithium-ion cells work in practice. But before we sign off, we might just talk about charging. Okay, so once you've used, let's say, your mobile phone, all the lithium atoms that were here, they've all gone, and they've turned into lithium ions, which are now all in the lattice, because you've turned your cobalt dioxide into lithium cobalt dioxide. All right, and so this is what the electrodes look like once your batteries run out and you have to charge it up again. So when you charge it up again, you apply a potential difference to the two electrodes, right? So you're going to make using the a power pack in class or at home, you're going to use the electrical socket to make this electrode very negative. And so what happens is that these lithium ions are forced, they're mobile, of course, because they're small, they are forced to leave and make their way over to here, where they receive an electron. Right, so let's say this electron here jumps onto one of those lithium ions, and it's going to turn into a neutral lithium atom. All right, so that's what happens during charging. And your phone, for example, is fully charged when you've completed that process. So you've basically taken all these lithium 1+ ions and you've turned them into lithium atoms, and you've moved them one by one all over here. So you've filled up your lithium atoms in the carbon lattice here, and you've disappeared them from the lithium cobalt oxide, and you've turned this electrode back into just poor old cobalt dioxide, where your cobalt is back to being a 4+ ion and a little bit unhappy, and your lithium is back to being lithium metal, also a little bit unhappy. It wants to be the lithium 1+ ion, and cobalt wants to be the cobalt 3+ ion, and so when you're using your phone, for example, you are facilitating lithium getting a bit happier by becoming lithium 1+ ions, and cobalt becoming a little bit happier, going from 4+ to 3+, and in return, for letting lithium and cobalt do that, the battery allows you to use your phone with power. Okay, so that's discharging, and I won't write the half reactions down. They're just the opposite of the reactions we wrote down on the previous slide for discharge. So there we have it. Hopefully that's been clear.